Okay, so we can get started. So just to status update on the class in sequence. So what's happening next is programming assignment 1 is due tomorrow evening, 10 p.m. Who's all done? Who's all done except for the last part, balanced? Okay, good. We're making good progress. Kind of looking beyond the next programming assignment, what's coming up next is starting next week. In the classroom, we're going to head into the data representation chapter of this course, all about bits and bytes, integers, and floating point numbers. And that whole unit will be fair game for the midterm exam, which is going to be immediately after spring break. So kind of to follow along in the reading, what you'll want to do is to check the syllabus, which is linked from Canvas. It's on my personal webpage, and do the reading around integers, bits and bytes, just so that you also have kind of a background of knowledge from the book to follow along. So that's class content stuff. The third quiz is already out and is ongoing. That's due next Wednesday. So I staggered this quiz and the program assignment this time so that they're not all due at the same evening. And then looking just beyond that, programming assignment 2 is also out now. Well, it's not quite out. It's going to be open, published tomorrow morning. So if you're all done with programming assignment 1, you can take a look at programming assignment 2. So with programming assignment 2, that starts to be one of the heavy-hitting PAs. So PA0, PA1 were both relatively lighter weight. Programming assignment 2 is going to be a full 150 points, 6 parts to it. That programming assignment 2 is going to be all about review of data structures. So most of it is about graph algorithms that you learned in CS 112, this time in C. And the final part of it is about a hash table. So all very good review of important data structures concepts. So that's good. That's a very long-range view of what's coming up in the class. What we'll do now is a kind of 2-part in-depth study, basically to close out what we have to know about pointers and allocating and deallocating memory. This is really just like mastery of the concepts. You know, we've followed this methodology in the class so far, right? We've been taking very careful steps with the pointers.c lab. And every line of code, we're able to draw a picture in the memory to fully understand what's going on and understand why there may be bugs and why the code has to be the way it is for it to do the effect that you desire. So strictly speaking, and consider the stuff that we're going to do today kind of just all optional, right? What do I mean by optional, right? You know the principles already. All of this is just further in-depth study, right? So one part of the in-depth study is, as part of the programming assignment, you'll experience using the stack data structure, right? We give you the C code that already implements the stack, right? And you can kind of explain using the picture that we have been drawing to explain why the stack works the way it does. But kind of the deeper next level understanding is, well, could we have written the stack in some other way, right? Could we somehow made it look even simpler, right? And the thesis of this is the stack implementation I gave you is the minimum required, right? It has to be written that way to achieve the data structure that you want to build, right? So today's study, the first part of that study is about that. And then beyond that are just kind of some notes on common bugs that we might encounter writing programs around pointers and memory allocation, freeing. Nothing too much to take a look at here. This is just kind of discussion material, right? So this is just all to close out our memory model in C, pointers, allocating, free, and getting ready for next week where we'll launch into bits and bytes, representing data, right? So that's just kind of frame where we are. So one new concept that we wanted to just review in C is that C is old. It doesn't have object orientation the same way that Java does. But nonetheless, when they designed the C language, they already realized that it would be useful to bundle different fields of data together and give that a type name. And so the way we achieve that in C is through this language feature called structs. Structs are like arrays, so whereas arrays would have been sequences of data, all of the same type, for structs, you specify what types of fields each struct has. And then there's just some syntax, right? So one common thing that we have to do when we're writing code around structs is you would have a pointer to the struct type. So here we have a type of struct called BST node, binary search tree node. You have a pointer to one such struct called root. And a very common thing that you'll want to do is dereference root, right? If you dereference root, you put the star root. This ends up being a BST node. And then once you have the BST node, you want to access a field inside that struct. So just like in Java, when you have objects and you want to get the field inside the object, you say the dot operator. Well, that came from C, right? You have your struct, you say dot, give me the key. And this is such a common idiom where you dereference a pointer and get the contents that they gave us some syntactic sugar. Right? Syntactic sugar just means a cleaner, quicker way, shorthand, shortcut way to write the same code, which is to use this pointer arrow syntax. Right? So this means dereference root and immediately also get the sub-element, get the field inside the BST node. So that was review. And the next sequence of slides, right? So the next sequence of slides is all going to be about the stack.c code example, which, right, if you've started to tackle balanced, the third part of the programming assignment, this is the data structure you need to do that part of the assignment. This is perfectly good code, right? This code works the way it's implemented. But the thing we want to fixate on is we need to explain to ourselves, why does it have to be written in this way? Right? Here I'm highlighting this very strange pointer to a pointer. Right? And this is something that we could just hand wave and say, well, it works, so it works. But I think it's helpful for us to really consider why any other more simple way of writing this would not work. So if you look at the slides, basically the next sequence of 6 slides is just kind of this study of several versions of code. I'll summarize why they don't work versus the 2 that do work. We can look at the slides, but let's just run this practicum, this laboratory, in our code live. Right, so let me just double check that all of this is functioning correctly. Right, so right now we have the perfectly functionally correct version of the stack. And a naive thing is, well, our first attempt at writing a stack, I'm going to now give you the first of 4 incorrect ways of making this code. So the first incorrect way is, well, we want to give the push function of the stack our struct element, right? So let's just pass it in, where param root is where the stack is held currently in memory. And then once we change this function signature, I have to kind of go through and make sure that the code will compile. So this just entails kind of making it so that the types match up correctly, just for the sake of compiling. And just to emphasize, right, this is incorrect code, right? We're tempted to write the stack in this fashion. Right, so I've implemented an incorrect version of stack, where the push function just simply takes the struct element directly. Let's compile and run this test case. And this will fail, right? And specifically, the kind of failure that we have this around is that we have a segmentation fault. We have access to a non-existent piece of memory. So let's draw what's going on, right? So here I have a new sheet in our pointers notes, our spreadsheet. And following our methodology, we want to write down, wherever relevant, what's happening in the memory, right? So the first thing I want to write down is in the main function, I've got this line of code here. So what's our methodology here? What's the data type? Data type of line 50. Come on, we were pretty good at this, yeah. Yeah, it's a pointer to a data type called struct element, name of the variable. And where does it live? We don't know, but we could find out. I don't think it's interesting. If we did print out what the value of root is, it's going to be a pointer data type. Its location is going to be in the memory stack portion of the memory, and it's going to be a stack frame corresponding to the main function. And the contents of this part of the memory, what is it going to be currently? Yeah, null. Right? Null is just a name for the number 0. So right now it's a pointer to address 0 all the way up here, 0x66x, right? It's just a pointer indicating this memory address here. Yeah, you have a question?
So simply adding the little star to the end of a data type turns it into a pointer value?
That's right, right? So the data type here, the data type right now for root, the data type is a pointer to struct element. Yeah. So you can add the star operator, the star syntax, to any data type. It could be an integer, it could be a floating point number. Here, the data that's being pointed at is a data type called struct element. Okay, so let's run the code and figure out why, when we run this code, it exits with a kernel, with a segmentation fault. Yeah.
Just a question. So element is defined above, or we define like struct element. But when we use the data type, like what was it, like stack, like struct stack, like that's like an actual type, right? So does struct have like different types, kind of, or?
So to clarify, right? To clarify, struct is just kind of a keyword. Struct is actually a part of the C language. Right? So if you look at the highlighting in my text editor here, struct is color-coded in a way indicating that it's a reserved word. Right? Remember in Java, there's these things called reserved words. Struct is a reserved word in C, in that you cannot name variables to be called struct. You can't say, I want a struct called struct. It will be like, that doesn't make sense. Element, on the other hand, is a name that we gave this type of struct. So there's many kinds of structs that we want to create types of. This data type here is called a struct element. And what are important things to, what is the point of a data type? I think this is worth kind of dwelling 1 minute on. Here we've created basically for the first time our own data type. Yeah, I think that's the right statement for the first time. What's the important information that a data type needs to convey to the compiler or to the program runtime? Like what's so important about a data type? Yeah.
It represents how our data is being shared or displayed.
It represents how data is shared or displayed. Good. What else? Yeah.
It determines how much space it takes to store.
Good. That's the first most important part that needs to be specified, which is given this data type, it tells you how it should be stored in memory. How much space does it occupy? In this case, just looking at the shape of this, we know that struct element, at the minimum, it has to have space to store an integer, and it has to have space to store a pointer. What other information does a data type convey? Well, to the compiler, what a data type can convey is what are valid operations you can perform on it. So for example, previously in this class, we've done demos where we try to, say, dereference a plain old integer. Right? I create an integer called 3000. I said, I'd like to dereference 3000. And the compiler will immediately catch that and say, that's not a valid thing you can do with a plain old integer. You can only dereference pointers. Right? So that's the data type in action. The compiler can examine the data type and say, does that make sense in this part of your code, in your language? Right? Data types are just basically parts of speech. Just like in parts of speech, you wouldn't put a noun where a verb is or a verb where a noun is. These rules on what types of parts of speech or the data types play a role in programming languages. Okay, so let's trace through the code now and figure out why this version of code just does not work. So we're in main. We've drawn what's happening on line 50. And as we run through, and we want to push a number onto the stack, well, immediately here we have the line of code that offends. Right? So what's going to happen when this executes? What's the value of the root right now? Yeah, null. And what does the star operator here, dereference operator, do?
Oh, right. It's gonna try to find the contents of a null address, and that doesn't work.
It's going to find the contents of a null address. It's going to go to this address, which is the address 0. The star operator tries to get the contents at that address, and this is the classic null pointer exception. Null pointer, null reference, right? You're accessing memory that is not valid. So that's the first version of code. It's incorrect. And it's incorrect for a pretty straightforward reason, right? So let's move on to the second of 4 versions of code, which is incorrect. Right? The second of 4 versions is going to be one where instead of having a pointer to a pointer, we just pass it one level of indirection. Right? This will get us a little bit farther, but it's still incorrect. So let's attempt that. We realize that to make this correct, what we're really trying to do is, we want to point to locations in the heap that store our data structure. So naively, we say, OK, well, probably we could do it with just one level of indirection. So let's give that a try. right? So I've made adjustments to the code so that all the data types all line up. I'll compile and run again. And this time it fails with a different type of error. This time around, program runs through, but it says that there's a memory leak. There's been memory that's been allocated but never freed. So let's go to our picture now and see if we can explain why that's so. So same thing, line 50, the record of where the data structure is still good. And we will run push, which will pass in all this information as expected. So let's go up to the push function. And now we can trace through line by line in push to see what happens in our picture. So the first thing it does is it mallocs some. So first thing that happens is, first of all, we now enter a new frame, right? So we're no longer in the main function, but rather we are in a new frame of memory. Corresponding to the call to push. And every function, the way it's written, the shape of the function, what variables are declared in it, dictates what shape the function frame will be, right? So in this function, there's already some things that we can kind of put down, right? So and when we call into push, there's going to be parameters for this function. So it'll reserve some space for that. It will have an integer, the number, which is a variable that's part of this function. And there is also a variable of type struct element pointer, which is called new element. So new element, once we reach line 17, what's going to be stored here? Right, so what does malloc do? Yeah. Yeah, so it's going to create a segment in the heap. It will find some address where there's enough space, say 6 something. And it will, at this location, prepare a sufficient amount of space to create a struct element. And what constitutes the struct element, right? So here we have the space for a struct element. Well, we have a integer, and we have a pointer to a subsequent element called next, right, forming a linked list. So this part in the heap here, these couple lines that I've boxed together, emphasizes that this is what struct element looks like. Right, and here in this case, I'm no longer being pedantic on how many cells I'm drawing in Excel anymore. We're a little bit farther than that, but any estimates to how tall, at the very least, struct element should be? Yeah.
Maybe 12.
At the very least 12, right? Because it's got a 4-byte integer and a 8-byte pointer. So at the very least, struct element really would occupy 12 bytes. So good, malloc just called. It plopped down some space in the heap to store a struct element, and it returns, malloc returns a pointer data type, and that gets recorded in the field called new element. And the rest of this code the rest of this code is just swapping some values around, right? So first of all, it goes to new element. And here we have the arrow notation. So arrow notation, again, means, first of all, dereference this address, go up to here. Now we're in a struct element. And once there, access the number field, which is right here, and record number. So say 12, right? Or whatever the text file input will specify. And then next, perform this line, right? So again, go to new element, dereference that location. We're now in the heap at where struct element that just got mallocated is at. Go to its next field, so that's here. And over there, write down the value of param root. So we got to now trace, right? So what was passed in as param root at the very beginning? Good. So push was called with root, and at the very beginning of this code, what is root? Null, right? So when we called into push here, this is push's function call frame, all this information got plopped in, right? So null was used to call and specified in param root. The number that you read from the text file is also passed in into the function. And up here, this line of code will just kind of move the data into the right place, right? So this null then gets also written down here. So you look at this frame here, and what does this tell you? Right? We've created a node, and its linked list pointer to the next element is null. So what does that mean? Yeah. Yeah, so this is exactly the end of the linked list, right? This makes sense. We're creating a stack. We've only put one element onto the stack, so is there any subsequent element? No, right? So we've created the sole element of a linked list, and it is pointing at nothing. And then, good. So then finally, kind of the kicker of why this doesn't work is I've got param root, so back in our function call frame. It's going to record in param root the address of new element, or the value that is new element, which is the address of the struct element. It records there, and we're all done. This returns. So what happens when we return?
The push frame gets popped off the stack.
Yeah, so this whole frame that is the push function gets popped off of the memory stack. So all this disappears. The box also disappears. And now we're back in the main function. So in the main function, it's almost as if nothing had happened, right? The root of the stack is still nowhere. And this program will happily create a bunch of new frames in the heap, but it's not actually implementing a connected linked list, right? So in our version of code that ran here, it says that there was a memory leak, right? So why was there a memory leak? Yeah.
Because we never freed the contents of the heap.
We never freed the contents of the heap. In fact, we have no way to free it anymore, right? This record of where this dangling linked list node is, we have no record of it anymore. We don't know where it is. So that's one way this program could have failed, right? And in fact, we were quite lucky that this program even ran as far as to the end, because there is actually no stack taking place. If we take a look at what test case we ran it on, right, I'll bet that what we're seeing is that the test case is just pretty straightforward, right? The test case in test 0 is just a single number pushed on and immediately popped off, right? So we never even simulated the case where we want to create multiple nodes in the linked list. I'll bet you that if we ran this via the autograder mode to check if the program is giving, to check if the program is not just like running to the end, but in fact giving correct results, this will fail in the sense that the program is just incorrect. Right, so for example, if we ran this on test case 1, it just reports that the stack is empty, the stack is empty, the stack is empty, which is not at all what is expected of the correct answer for test case 1, which is that it should report some result. Anyway, so there's no stack actually being built here. Good. Shall we move on? So that was version 2 of 4 that are incorrect. Yeah.
So when the frame is popped up, or the call frame is popped up in stack, that means that that's sort of a race to memory. So since we set parameter equals to new element, that should be safe.
Say that again?
Since we set parameter equal to new element in the function frame, and since that was popped up, that doesn't save because we need the pointer.
So when push returns, right, we had set param root to new element, but as far as where all this is recorded, param root is an argument to push. Its record is written as part of the push's call frame, and so it has nothing to do with the value that's stored in the main function. Yeah? Can we make struct elements without using malloc? So where would it be stored? Okay, so let's devise a different idea, which is, what if we just declare that we would like to make a frame called new element. It is of type struct element, which means that here we're storing a new element, and as part of, we're recording it as part of the stack frame, right? So we could, instead of having all of this being put in heap, you're proposing, like, let's just write it down so that the new element is just a function field of the call frame, right? So sure, we can perform something akin to this. I haven't fixed up this code so that it compiles, but you're proposing something like this. So what happens? Same. Once this returns, what happens? Yeah.
It gets popped off along with the rest of the function, so it doesn't save.
Yeah, so once push returns, the carefully crafted struct element is also deleted. Right? So that's why you can't, that's why anything that is dynamic, right? Any data structure that's going to grow and shrink in size has to reside in the heap. Right? The heap persists. The stack, the stuff in the stack, right? What the stack is doing is it's keeping track of what's happening in the program. Right? The stack in languages like C and Java and Python and everything that derived from C, the memory stack here, its role is to enable recursion. It's enabling function calls. Right? It's keeping track of how functions are calling each other. And so there's a very strict discipline to how big a call frame is and what happens when the call frame exits. Right? It grows and shrinks according to how deep into the function calls you are. Okay, so now let's move to version 3 of 4 that are incorrect. So version 3 or 4 that is going to be incorrect is going to observe this, right? It will say, okay, well, if the whole issue was that the struct element that we created is not being properly returned to main, well, how about we propose that we just return it explicitly, right? How about we do this? How about we return the struct element we created? Would that work? So for this, let's go ahead and try implementing such a version of code. So what we're proposing is let's return struct element push. Let me roll back the code even more, all the way to plain. Right, so we're proposing, like, let's make push return the struct element that we've constructed, and let's make param root get passed in as the raw data type, just the plain old struct element. Param root is going to have to be made like this. And push's function shape has changed, so it has to be passed in like this. And the idea is we want to assign root to be that. And the idea is we want to assign root to be the location of returned element. Right, let me double check if this compiles. So first of all, line 22, this return is no longer returning void, so we actually have to return what is intended to be returned, which is this whole element that we've created. And line 59, there's just a syntax error. Wow, it's really unhappy. Returned element. Oh, this is supposed to be grabbing the pointer of. Okay, so miraculously figure out a way to compile this incredibly incorrect code. So let's see how this derails, right? So what changes have I made? I've made push to return this allocated struct element. We intend to return struct elements, and we're going to, in the main function, capture what is being returned. And as kind of a study that I'll do right now is I will declare the struct element that we would like to capture, right? So the struct element. And I would like to also print out where such a variable lives. Actually, never mind. This is perfectly fine. Okay, good. And then as part of the exercise of updating the actual data structure, I'll assign root to wherever this returned element lives. Right? This is going to go very sideways. Right? This is very strange code. But the whole goal is, well, let's see if this would work. Right? We're attempting to return struct elements, so let's return it. So let's go to our picture, or rather, let's try running this and experience how it fails. So this time around, this is a segmentation fault where something along the lines of we are accessing incorrect memory. Right, so who wants to kind of fast forward and say, why is this failing? Right, we don't have to study this version of code too much right now because it fails in a very familiar way. So in our picture, just to roll back to a correct state, we're in the main function. Main function has the line, the code at line 50, which declares struct element pointer, data type name is root, its value is null, and here we're calling push, and the way that we're calling push is we're just giving it a struct element, so we try to dereference root. So what's the bug? Yeah. Yeah, so performing this operation will take the value of root, which is just a fancy name for 0. It will try to dereference the memory at location 0, and it immediately has a memory access error, right? So this was version 3 of 4 that is incorrect. Let's move to version 4 of 4 that is incorrect. Yeah? Okay. So version 4 of 4 that is incorrect is just to fix this star problem, which is, well, okay, how about we add one level indirection to the way we pass in root. So what that will do is this becomes a pointer type again. Good. And push, the way we call push changes. There. And let's make sure that this compiles. It compiles, great. And let's run. Okay, so we get a different kind of error. This time is called stack use after scope on address. We've never encountered something like this before. So this should be pretty fun to study and follow along why it complains the way it does. Right, so what's our methodology? We've got in main function, line 50, good. That's the state of our memory at this line. We're going to call push. So calling push, we now create the frame that is the push call frame. And then we should also take note of what's being specified here, right? So I mentioned that every time you call a function, that creates a call frame, a function frame on the memory stack, and it lays out all the fields that are mentioned in that function, right? So now, in this version of main, there is a new field. What's the new field? There's a new field here. Yeah, go for it. Just shout it out.
It's a struct element type, the name return element.
Yeah, so I'm anticipating that my call to push is going to return to me, and I'll record in main my returned element. And just to emphasize that, yep, this is in fact a struct, I'll record that as, okay, this is a struct elements int. Right, so I'm just going to use this very strange informal notation that this return type is a struct element. And because it is a struct element return type, it has all the contents of what make up a struct element. Right, so a struct element type has inside it an integer called number, and inside the struct element, you've got a pointer to another struct element that's called next. And so this main function here, its call frame now has these additional spots where we anticipate to record whatever is returned back from push. So now let's actually descend into push, right? So we're going into push, and again, step by step, trace through what gets built up. So same discipline, every time you call a new function, all the things that are mentioned in the function, the shape of the function dictates what is put on the memory, right? Stack discipline. So we've got the parameters being called in. When we call push for the first time here, what gets populated in is the roots value. So null gets copied into there. Our number also gets populated in. Say 12 in this test case. And it calls malloc. Malloc goes up into the heap and creates a struct element. And it creates the space for struct element, which also has a pointer to the next struct element. And its name is called next. Very good. Malloc will return wherever this exists in memory, so 0x6. And this gets recorded as a field in the frame of struct element, of push. Right, so here we have the record, call new element, and still on this line of code, right, line 17, it made all this allocation, and it writes down, great, there you go, boss. You've got your struct element set up in the heap. The next few lines of code is just, again, moving some numbers around. So we got to populate our newly created new element, jot down that number, jot down its next pointer. This is the tail end of the stack, so it points to nothing, which is indicated by the fact that this was called with param root being null. And next, it makes a record of all of this. So param root gets written in like so. And then this is finally something new and interesting will happen, right? So what will happen on this line of code? We're about to exit push now. We've reached the end of push, and it's about to return. But this time around, push returns a value. The value's data type is struct element. So what happens now? Right, this is something new that we're seeing, right? So this has been tedious to get to here, but actually there's a kernel of something cool and new that's happening that we haven't really elaborated before. What happens when the function returns? Okay, good. So pause there, right? So new element is this address. So it will dereference it. And in this case, dereferencing will get us this whole struct element. And I will copy that. Next, what happens? We're going to return, right? And return, where should the stuff that I've highlighted, where should that get put to? It gets returned into the main function, right? So it will take all that stuff and it will paste it into the struct element returned element here that's ready to receive the data. So I can copy all of this and paste it down here. Good. Next, yeah, question. The address is not going to be pasted. Good, right? The address is still going to be somewhere in the main function. Good clarification. Great, so we've returned, and what else happens when we return? We're about to return back to the main function, so this goes away. We're back in main. So this seems like progress, right? Who thinks that we've made progress here? Yeah, why do you think we've made progress?
Because now the data from the method is also being saved.
Yeah, so let's take stock of like what we've gotten right so far, right? We've made some progress. This is the 4th of 4 versions of code that are wrong. It's still wrong, but at least there's some things that look better now. So first of all, successfully, we've got a data structure made in the heap. Good, so that persists. This time around, we've got a record of that data structure now also living in our main function, so that's pretty nice. And then now we're going to go sideways, right? Now this is all going to go haywire. So what happens next? Here, this line of code, we're going to assign root. We're going to assign root, right, where we hold on to our data structure, and we will write down, hey, great, we called push, and push gave us a data structure, and let's write down where that data structure is. So what will this line of code do? First of all, what's this segment going to do? Ampersand returned element. Yeah.
Address of returned element.
Yeah, so it's going to get the address of returned element. Great. But this address, right, just as you had clarified, right, this address here, where is this referring to? This is just referring to the location of the variable called return element. So it will take this value and put it in root. Yeah, so we're not actually pointing at the heap. Right? This whole effort of creating all this in the heap, we're not actually pointing at it. Right? So already there's going to be what type of bug? Yeah. Sorry? First of all, there's going to be a memory leak, right? Because this knowledge that in the heap there was this frame allocated at 0x6 whatever, we don't know about that anymore in the main function. So first of all, there will be a memory leak. Yeah.
And also, if you were to keep pushing things onto the stack, since the address of returned element isn't changing, it would successfully, each element would have a distinct address, right?
Each element wouldn't have a distinct address. So do you think it's worthwhile for us to step through a little bit more just to see how it keeps going sideways? Who wants to do that? Or who thinks let's just move on? Who wants to keep going and see how it breaks more? Okay, let me try doing this in 2 minutes, right? So we keep running this loop, right? So we've successfully made one frame, and we intend to continue pushing more elements onto the stack. So this loop reads in the next line of what has to be pushed. And once again, we are in the position where we have to call push with these arguments, right? So we're about to call push, and so we do our discipline of we're about to call push, and calling push will create push's call frame, which will set it up the call frame. It will pass in a number, and it will be ready to record location of whatever gets allocated. And it will, as part of calling push, will copy into that function the correct parameters, right? So first of all, it's going to take root, and it will put this as root, and number. This time around, we read some other number, say 24, which will be pushed onto the function, pushed onto the stack. And it will go allocate some more memory for another element, say here, and it will record all this stuff.
Professor,
Yeah,
how does it know not to go to where the previous stuff is?
sorry.
Like, because there's no, of the previous, like, first number, there's no way to access it anymore, right? How does it know not to, like, just put it where the previous stuff is?
Good question. How does malloc know not to just malloc over the previous, right? So malloc is a C library function. So within malloc, it has a table called the allocation table, which keeps track of what's been allocated. Right, now that kind of raises a very good question, right? So if malloc will go through this whole effort of keeping track of what's been allocated, why not just use that record to somehow allow it to do automatic freeing, right? And that's kind of the tricky thing. Java invests a lot of sophistication and kind of language analysis to keep track of when pointers are no longer valid, right? So when Java creates an object, it will keep track of if that object is still alive, and if it sees any object that is no longer alive, no longer accessible, it will free the object space. In C, it takes a different approach, right? It's able to figure out what's been allocated, but the responsibility of knowing when space in the heap is no longer useful, that responsibility belongs to the programmer, right? That's why we have to call malloc and free. Okay. Good. Right, so where are we so far? Right, so far I've copied into the new frame all of this as called. And I believe we should be able to return this line now. Here, right? I'm not going to keep running this simulation any further, right? The point is, it's not correctly forming a correct data structure. Why? What are some symptoms we already know it's not forming a correct data structure? Yeah.
The fact that there is a memory, like, heap that's not, like, maintaining, like, there's no way to access the previous numbers.
So let's do this, right? So suppose that we now want to walk through this linked list. I walk through this linked list, and first of all, I want to traverse the linked list. The root element field tells me my linked list begins here, and I want to go to the next element, and already it concludes that the linked list is only one element long, right? But really up here, we expect that there's two elements to the linked list. So the linked list is not being correctly linked up. Even if you somehow had access to this struct element here, right? You traverse it as a linked list. You start with this node. You go to its next. Where does next point to? Yeah.
Points back to the stack.
Yeah, it points back in the stack, right? It's not pointing to the next element of the linked list as it should be. Right, so we try running this. It's going to have some kind of, this case, it's telling us this type of error. It says that there's a stack use over scope error, which means that somewhere in running this simulation, we're going to have some peculiar situation where we're going to dereference an address which belongs to a stack call frame, which is no longer active, right? So somehow we keep running the simulation, it's going to encounter that. So we've done 4 versions of code that are bad, right? 4 versions of the code that are bad. And there's a further lesson here, right? Further lesson here is all of these symptoms that we see could be summarized in these later slides. So we're never going to we don't have time to get to these bottom slides here, but these bottom slides here just summarize a lot of the same talking points that I'm talking about. referring to memory that doesn't exist, dangling pointers that never get freed, dereferencing pointers that point to null. These are very common memory errors, and by studying 4 versions of code which are incorrect, we encounter all of them. Right, so now finally, let's go to the 5th version of code and the 6th version of code, which are correct. So let's study this one first, because the way we have the code right now is pretty close to doing this already. Right, so looking at this here, who wants to just kind of quickly guess why this version of code will succeed? Yeah.
It returns a pointer, so the main method, or the main, I guess, call frame can access the heap
Good.
instead of just copying data over and leaving it in the heap.
Good. Right, so let's implement this version of code. So instead of returning the whole struct element now, we're going to return a pointer to whatever is allocated. So the return type is now just this. And the call shape to push, the call to push, the thing that we are expecting, the return type is also going to be a pointer. And assigning that return type to root just looks like this. This should be good. I can make, and I'm bold enough to just run the autograder, and this will succeed. Right, ta-da, this version of code is great. And in fact, this version of code is different from what we started with. Right? When we started class, the version of code is actually version 5. Here is another way that is correct. Right? The difference between 5 and 6, I kind of make this pointer and I put it at the return. So let's study why this works. Right? Is that surprising? Comparing 5 and 6, is it surprising that 6 is also correct? So, right? If it's correct, then it's correct. So let's do our simulation, right? Our discipline in figuring out what's happening. So we should be able to run this pretty quickly now. This is just going to be limited my typing speed. So what's changed? The shape of main. So when we call main, any function call sets up the call frame, records all the fields that's going to be there. But what's different this time? So this time, main is expecting a struct element pointer called return element. And it no longer reserves all the space for a whole struct element like we had before. And at the beginning, root is null. We call into push. So now we're in push. Calling into push sets up, as part of the discipline, all the fields that show up in the shape of the function that is push. And as the process of calling push, it populates the arguments of the function. So null for param root, 12 is the number we want to push onto the stack. And good. malloc goes off, finds a suitable plot of memory to create our struct element. So struct element consists of an integer and a pointer called number and next, respectively. It allocates all this space at an address called 0x6 something. Calling malloc returns that address, and it says, here you go, boss. there you have a struct element located at 0x6 something. The subsequent lines of code populates your struct element with the correct data. So integer records as 12. The next pointer is null, indicating that this is the last element in the linked list. And here we write down param root as 6 something. And then finally, as return. Now we're at the interesting part, right? So I fast forward as quick as we can to get to this interesting part, which is this version of code. We're about to return from push, and what's going to happen? Yeah. We've now, this time around, returned an address in the heap, right? So we're about to exit push, and as part of returning from this function, whatever gets returned from push is going to be recorded as returned element in the main function. And this time around, it records 0x6 something. And we exit from push. Right? So we've made much better progress this time. So what's the better progress that we've made this time? Yeah.
Your name is accessing rather than what's inside this stack.
Yeah, so in main, this time around, we've got finally a pointer to the newly allocated struct element. And in fact, even better, on the next line of code, I will update root to point to the same location. Right, so we've got that good taken care of. So what symptom already do we take care of? No more memory leaks, right? The calls to pop will see the right addresses, and it will be able to free the heap correctly. And then what other nice thing is going to happen? I keep pushing more elements onto the data structure stack. It forms a linked list, right? So the next call to push creates a new frame. Its number is 24. Its next element is going to point to whatever is passed in as param root. And we form a correct linked list, right? And root will be updated to this. So this time around, right, this is after simulating, let's push another element onto the stack. You chase the pointers. You say, I want to see what's on the stack. You go to root. Root points to this frame, which is the top of the stack data structure. At the top of the data structure, you've got 24. And you pop that off, what becomes the new top of the stack? Pointer to 0x6000, right? So it points to the next element of the stack data structure. Yeah.
Will returned element also get updated to the new address?
Where?
Like in the stacks, the returned element, would that also be 610?
Yeah, there you go. Okay, so great, right? So this version of code works. Quick poll, who likes this version of code? Who likes this version of code? So half and half of those who have an opinion. The rest are like, oh, who cares? They're both correct. Stylistically, what's the difference? So stylistically, what's the difference? Why did I provide this version? Version 5. Yeah.
So 5 is a void, so you can't access the original function. The specific but it hides that the specific function that you can get it from
Yeah. All right, so I'll make argument here, right? This is a very subtle thing. This is style. This is pure code quality issues at this point. Both versions of code are equally correct, right? And in fact, if you're only considering writing push, right? If all I care about is to be able to push stuff onto the stack, I would indeed argue. I would argue version 6 is better. Right? Version 6, if only looked upon just in terms of the push function, version 6 is nice. Why? Because the things are where we expect it to be, right? The return type is what we expect it to be. It returns a pointer to a new stack frame, right? You read this, you immediately kind of know what's going on. And as an argument to the function, as an input to the function, we also give it a pointer to a stack frame, right? So taken by itself, version 6 is better than version 5, right? But why did I give you version 5 then, right? Why is version 5 seemingly less intuitive? Well, what does it mean for it to return void? We see return void, we think it returns nothing, right? It has no effect. And then we go into this other rabbit hole of what does it mean for this to be a double pointer? So why is it that I gave version 5? Yeah.
It's a lot more like pop, or like where like you aren't returning anything, you're just like you're doing something to a linked list rather than returning a part of a linked list.
That's exactly correct, right? It has to do with the fact that push is paired with pop. So as kind of a code style issue, right, I want push and pop to have the same shape, to look the same and feel the same, right? And when we go and write pop, what happens in pop? Right? Pop not only just takes an input anymore and updates the data structure, it also has an additional output, right? What's the additional output that pop has to do? Yeah.
The int that gets popped off.
Yeah, it has to report what just got popped off of the stack, right? So for the pop function signature, I have a higher priority thing that I want it to report, which is the integer return type, right? And C is a old school language, right? How many fields can Java return? Yeah. As many as possible? Is that true? Wow, Java's gotten really good. How many returns can Java return? 1. Java can only return 1 data field, right? Maybe you can create an object, and Java can return objects. What's a language where you can return as many things as you wish? This is kind of outside the scope of this class now, but for those who have some experience in other languages, what's a language where you can return as much stuff as you wish? Yeah. Yeah, Python can return tuples. So Python can return 1,000 things at once, so long as you can keep track of the sequence of all of it. C and Java are only single return. So when we have this situation where I've got pop, pop has 2 effects, right? It first has to report what the integer is, and also it has to give you the updated data structure. Well, these 2 things compete, right? We want to return 2 things at once. The higher priority thing that should be returned is the integer that got popped off. And all the other side effects we have to implement by passing by reference, right? So this is why pop looks like the way it does. And since pop, that function looks the way it does, between push and pop, we want the 2 functions to look similar. So taken together, the argument would be, well, our original version of code, where push looks like this, is the best choice for implementing push and pop. All right, I hope that made sense. That was all just code quality issues. Any questions up to this point? Yeah.
Just a clarification, so number 5 would be passed by reference, right? And then number 6 passed by value because number 5 is modifying the actual value.
So I think basically your question now is, so why is version 5 correct? No, not quite.
No, I mean, I get that it's modifying like the actual stack, like directly, not returning it and then setting it to what we have. But isn't that passing by reference technically?
You're asking why is 5 correct, right? So let's take 6 minutes and run a simulation for version 5. Right? So version 5 is I've undone the whole code. We're back to the exact same stack data structure that you have in your repository. It compiles and run, this is correct. And we should draw a picture of why version 5 is correct. Right, so version 5 is correct because we are about to call push. The root of the data structure is null, so the data structure is empty. We're about to call push. Push, when we call push, stack discipline, push expects a data type called struct element star star, called param root, and a argument for the integer that will be pushed onto the stack. And it will create a placeholder for a pointer to what will be allocated on the memory. And as a process of calling push, it writes in all the correct information. Right? So number gets called in as 12, just like before. That's what's going to get pushed onto the stack. Here is the highlighted thing, right? So what happens here? What is the pointer value that gets passed in? Yeah.
The address of root
The address of root where?
in the main small brain in the stack.
The address of root, right? When we call push, push is being called with a address of operator applied to root. So it's going to go to root, which is here, get the address of, and this is what gets passed into the push function, right? So already something interesting and different has happened. Malloc goes off into heap as expected. It creates the space to write down a struct element. It records the number is 12. The next is going to be what's passed in as the end of the linked list, right? So here, new elements, next field is going to be a dereferenced value of param root, right? So it will go to param root, take this address, go to the contents at that address, right? So this null here is no longer a null that it knows about because null was passed in, but rather it's a null that it knows about because it went to go look in the main function's record of root and say, okay, null. And then good, so we're now on line 21. So line 21 is also important. So what happens here? What's new element? So new element is some address in the heap. It's at address 0x6 whatever. And where does that get recorded to? Yeah. So it will go to param root, which is this number here, a pointer. It dereferences that pointer. So what does it mean to dereference? Go to where that address is. Where is that? Yeah. So 0x7 whatever is in the main function call frame, right? So we dereference that location, and it writes down in the main function's call frame that in the heap we created a stacks data structure, right? This is passed by reference. We passed in a reference to a location in the main function. So that's where pass by reference is. Now, the kind of semantic thing is, well, what do we pass a reference of? Well, we passed a reference of a reference, right? We passed a reference of something that is itself a pointer. So this is why there is 2 stars here. And this is why this version of code is also correct. All right, so that's it. Time's up, right? So that wraps up basically what we need to know, a really in-depth study of memory allocation, how the stack and heap work, how functions return, and how you bring all these things together to build data structures. All right, good luck. Hi.
When you write to the Excel file, I
Yeah.
noticed that you write like bottom to top instead of top to bottom.
Ah, okay.